I've entitled this talk Interference and the Art of Static Correction. Now, the use of the word art for static correction, those of you who've been processing many years will realize that, in fact, it is very much an art. There's not a particular technique that works in every case. And in fact, there are some statics correction issues where almost nothing works. So I hope to show you one case of that today, of real data, and then I'll show you, in addition, a example of some data where ordinary statics corrections methods work, and yet the interferometry may, in fact, provide a somewhat better solution. Those of you who came expecting detailed mathematical arguments will be disappointed, because I prefer to use intuitive arguments and diagrams, and I hope this will suffice. I was mentioning to Julie on the way over here that I may have the distinction of having an article in Geophysics with the word interferometry in the title that has absolutely no mathematics in it. There's almost no others that I know of that can claim that. So let's get started. This is how I've broken this down. I first want to talk about the interferometry concept and hopefully relate it back to some things that you'll remember from your physics classes when you first heard about optical interferometry. Then I want to talk about something that you may not be familiar with. I'm going to expand the usual surface consistence notion that we use most often in statics to something I call the Raypath consistency. Then I'll combine those two to talk about Raypath interferometry, which is the formal name of the technique that I'm talking about today. Then I've got two examples, one from the Mackenzie Delta, where at the time that these data were processed, no other statics methods would work properly. So this technique is especially designed to deal with cases like that. Then I'll show you actually two examples from a more recent survey at Hussar that the cruise people, along with some of their sponsors, performed over a year ago. And I'll show you some results from that. Then I'll have some observations. Since I consider this an ongoing project, I don't want to talk about conclusions at this point. I think we're just beginning to see some of the potential and limitations of this, and I sort of want the option to be able to continue to work on this. So first of all, this is what we're going to be talking about when we refer to interferometry. A recorded wave field of some kind will be compared with a reference field by cross-correlation. Now that's a pretty simple concept. It's very analogous to what we will have seen as undergraduates in physics when we did our first interferometry and we looked for fringes between a reference beam and a probe beam of some kind. Now we'll take that further, however. In order to be useful, we'll take those cross correlations and derive inverse filters from them. And furthermore, we'll apply those inverse filters to the recorded wave field to correct the wavefront disturbances. Here's what I mean. I'll show you this in pictures. Consider the old optical experiment where you have basically undisturbed wavefronts from a common source, and you've got essentially, you're showing two of them here. And that just means that we've gone through a beam splitter or something to provide two of them. Now, on the left, we're showing a uniform medium, and on the right, we're showing an irregular medium of some kind. And we pass those undisturbed wavefronts through them, and we call this the reference wavefront, and this we're just referring to as a disturbed wavefront. Now, optical interferometry would cross-correlate these basically optically by shining them on the same screen or something like that, and this would be what you observe, the cross-correlations. That's what your optical fringes are. Now, as I say, we take this one step further, derive inverse filters from cross correlations. It's a standard mathematical procedure. And we take that disturbed wavefront and we apply those inverse filters, come up with a corrected wavefront. And if we've done our job perfectly, then that corrected wavefront will look very much like the reference wavefront or the undisturbed wavefront. So that's the concept that we're going to be using. And just for future reference, this little section that I put in the oval, this is what we're going to be calling pilot traces. Now that's a concept that most of you will be familiar with from other statics correction procedures. Now, let me go into a little more detail about what I'm referring to as interferometry. I've also referred to this as statics deconvolution. Back years ago when I was at Shell, I talked about this kind of idea. Basically, the notion is that a static shift is always an approximation, whereby a surface function that has to do with the surface layer, the effect of this is approximated just by a bulk shift of the seismic trace. We get rid of that surface function just by shifting the entire seismic trace that has to do with that particular surface location. Static shifts work for relatively simple surface layers, but for more complex surface layers, what we need to do is to estimate the surface function and deconvolve it. In other words, apply interferometry. Now, you can do this even if you still cling to the surface consistency notion. So the interferometry and the getting away from the surface consistency, those are two different concepts that are combined in this current technique that I'm talking about today. So let me show you once again, if we're recording seismic data and we have a surface with no weathered layer, and we're looking at a reflected wavefront from basically a single reflecting interface, we get a seismic trace that looks a lot like this. Basically quite clean until we have a spike indicating the location of the reflector. On the other hand, if we have a surface layer, and here I'm showing a simple, what I'm calling a simple surface layer or uniform, then we get a similar looking seismic trace, only now we find that the effect of the surface function, or the effect of the surface has been to shift the position of that reflected spike, just because this layer is typically slower. And so we call that the effect of the surface function. Now, if we have a more complex surface layer, in fact, we get something that looks more like this for seismic trace. And you look and see that's got actually several arrivals. Now, that is more difficult to correct for, and typically we correct it the same way we do for this kind of surface function, and that is just to shift the data. And usually the shift is related to, say, the maximum amplitude of that surface function. And what I'm proposing is what we really need to do to get to this desired reflection is to measure these things, derive an inverse filter for them, and apply those to the raw data to remove the statics. So that's the notion behind statics deconvolution. Just to go a little further on that, if we talk about a one-dimensional surface function, this stays still with the concept of surface consistency. The surface function will vary only with surface location. Surface consistency means that all the energy entering or emerging at a surface point basically has the same surface function. This is what we mean. As you well know, this is the picture we have for surface consistency. Any energy that is transmitted into or back from the deeper Earth basically traverses the near surface in a very narrow cone of raypaths. In fact, we often assume that it's virtually the same raypath. On the other hand, when the velocity of that near surface layer is larger than the velocity beneath, or even comparable to, we have a picture more like this, where these raypaths are not nearly the same. and in fact, energy transmitted along them doesn't come through a common ray path. So this is what we mean by not surface consistent. So in order to deal with this, what we really need to do is to go to the concept of a two-dimensional surface function, so that the function can vary with surface location and with ray path angle. So then when we talk about ray path consistency, this is the concept I'm trying to introduce, means that we have a common surface function for all energy entering or emerging at a surface point at a specific ray path. And then what we'll find is that surface consistency is just a special case of ray path consistency. Let's look at a diagram that shows this. Back to our surface consistent picture. If we decide now to talk about a two-dimensional surface function, this is what we'll get. And I'm indicating phi is the near surface ray path angle. If we plot the arrival times that are caused by this near surface layer, the delays caused by this near surface layer as a function of that angle, we'll find that basically the arrival times are all the same. So this is how we justify the use of the surface consistent static approach. We know that that surface function doesn't vary with angle, and we can approximate it with a single static shift. On the other hand, when we go to a picture like this, that changes what we mean by a two-dimensional or angle-dependent surface function. Now we see that we have a different static shift depending on which angle. And if we complicate things further by making a more complex surface layer, then we go to a picture like this, where in fact we have a different function, not just a spike, but an actual Earth function, surface function at each angle. And we could think of complicating that even more and making this near surface complexity actually vary laterally. Then each of these functional shapes would be different as well. So this is why we go to a two-dimensional surface function, is to accommodate a more general near surface layer. Now, how do we reorganize input data to take advantage of this so that we can actually analyze seismic data and help to remove this near surface function? Well, in the XT domain, source or receiver gatherers basically present the data as a function of surface location and offset. We're all familiar with this. And the offset is in units of distance. I'm going to propose that we use the radial trace transform to map XT data into the radial trace domain, where now the same data are presented as a function of surface location and near surface ray path angle. And the units there will be velocity, or slowness, if you like to go that route. Here's a picture to help you see. This would be basically what you see for a trace at a constant offset in the XT domain. And what you find is that this near surface angle basically changes as you go down in depth for the events on that particular seismic trace. So this shows you that data as we record them are not suited for this ray path approach. So we need, in fact, to transform the data into some domain where they are suitable. Now, I want to make sure that you understand the radial trace transform. This was a concept introduced by Claerbout many years ago. He basically introduced it for use in migration. If you transform your data into the radial trace domain and sort them off according to velocity, it turns out that there's certain kinds of migration that are much easier to perform in that domain. And Shell was one of the first to actually make use of that in some of their migration software some years ago. This is what the radial trace transform is. It's not an integral transform. It's not the radon transform or the tau p. People make this mistake, but it's not. The radial transform is just remapping. You basically remap the samples in the XT domain into samples in the radial trace domain. And the way you do that is by putting a grid or a fan of linear trajectories across the input gather, and along each trajectory you gather samples from the traces or you interpolate between them, and then you post the samples. Now I'm showing some numbered trajectories here, 1, 2, 3, 4, and 5. And if you go over to this diagram, you see where those come. The samples along trajectory number 1 would plot over here, and you notice that since we run off the edge of the gather before we run out of travel time, this is where this trace ends as well. For trajectory number 2, we would get a similar case, but it goes a little deeper in time. Likewise, for 3, you get more samples, and finally for 4 and 5, you essentially have them fully populated. Now I'm showing only a very sparse transform over here. Typically, we'll use thousands of traces in order that we don't alias the initial gather in going to the radial trace transform. Now, when we're in the radial trace domain, it turns out that this is very similar to this is, in fact, the geometry of a trace in that domain. It turns out that what you have done is you have mapped the data in such a way that the near surface angle is constant for all the reflections or all the events on that trace. Also, the emerging data comes back at the same angle. So you have, in fact, gone into a kind of constant angle domain, where that angle that you're talking about really relates to the radial trace trajectory, not necessarily to the physical. But anyway, this is what we go to. Now, let me talk about a common angle gather, which is basically just radial trace data resorted. The common angle gather is created by sorting all the collection of radial trace source or receiver gathers that you've generated by near surface raypath angle and surface location. They're analogous to common offset gathers in the XT domain. And once again, the near surface raypath angle is not necessarily constant for a common angle gather. This confusion has come up when I've talked about this topic in other occasions. And by that I mean, if you think of the near surface raypath angle as shown here for each different surface location, this would sort of be a near surface raypath plot for a common angle gather. But in fact, this is only true for a uniform surface layer. If you've got something like a low velocity zone, then those angles will vary as well. So really, a common angle gather is not a constant angle, but common raypath parameter would be a better way to talk about it, but I find that a little clumsy to use, so I'm going to continue to refer to these as common angle gathers. Now let me show you how we generate these and what one looks like in the real world. I've chosen 3 source gathers from the Mackenzie Delta data set that I'll be talking about shortly. And on the center one, I lay out a bunch of radial trace trajectories. Now this isn't all of them, but they're representative. And in particular, I'm going to look at this one at minus 492 meters per second. Now remember, this velocity is just a parameter. It has nothing to do with anything physical. It's just the angle at which we select the data for the radial trace transform. Now that center gather, when you go to the radial trace domain, looks like this. And we see that along the top, in fact, instead of offset, this is actually velocity, units of velocity. And so that red trace, that red trajectory, belongs right here. That's the trace at minus 492 meters per second. Okay, now if we take all the source gathers on the line and do the same thing to them, we'll have very similar looking gathers. And then if we further take all of the traces at 492 meters per second, put them in one panel, we get this. And that's where that particular trace belongs. But now on this gather, all the traces along here were picked with that particular surface parameter. They're all minus 492. Now, what this means is if we do this for all the data, then we have a series of these common angle gathers ranging in parameter velocity from, say, minus 1,000 meters per second up to plus 500, which were the parameters we used for the radial trace transform. And these gathers then are where we do the actual interferometry. Okay, this is, in a nutshell, what we mean by the Raypath interferometry method. We map the XT gathers, either source or receiver, to radial trace gathers, sort these traces to common angle gathers. Then we create a reference wave field, and this is what we're going to be talking about, pilot traces. Apply interferometry between the reference angle gathers and the raw angle gathers, and then we sort the corrected common angle gathers back to radial trace gathers, and then map them back to the original XT source or receiver gathers. So that, in a nutshell, is the Raypath interferometry method. We're going to spend a little time talking about how we create the reference traces. This is fairly key to how well this works. And I'll go into a little more detail about how the interferometry is actually applied. Okay, the interferometry process is described by this. We cross-correlate the raw common angle gather traces with pilot traces and hence estimate the surface functions for each common angle. Now, I'm implying that the cross-correlations are basically the surface functions, and that's true. The cross-correlations are one estimate of the surface function. We actually try to improve those estimates, and I'll talk about that in a little bit. We try to improve the estimates to make them broader band and to give better results. That's what this conditioning process is. We condition those functions to whiten them and suppress spurious events. Then we derive broadband inverse filters for each function and apply to the raw common angle traces. Now, I'm going to show you some synthetic data just to give you a feel for the interferometry process. This is a trace gather. I'm not going to specify whether it's a source gather or a receiver gather or, in fact, a common angle gather. It doesn't really matter for illustrating the interferometry process. There are 5 events, some of them more or less buried in the noise. You can easily see this prominent one here, and likewise I think you can see the one down here and maybe this one here. The other 2 are pretty difficult to see. The signal to noise, signal to random noise is 6 on this. Now, if we put some random statics in here, selected from a uniform distribution, those synthetic traces look like this. And now we can still see this main event here, but it gets a lot harder to detect some of these others. We can kind of see this one here. But these are very large statics. They range from plus to minus 150 milliseconds. So this is a fairly difficult problem. It certainly would be on real data. Now, here's how we create the pilot traces. Turns out that if you do a running trace average or a trace mix along an event horizon on the trace gathers, these make pretty good pilot traces. Now, doing this along an event horizon is quite key. You need to pick an event horizon just like you need to do this for most autostatics methods. So you don't get away from doing an initial interpretation of your data. And in fact, if you have structure in the section, and I'll show you this on the McKenzie delta data, then you have to pick a horizon in each distinct part of the section. So you may wind up picking 2 or perhaps 3 horizons to help guide this process. But you need to do the running trace average along event horizons with a smoothing length roughly one spread length. This is very much empirically determined, but one spread length seems to work. One other thing that works is if you have very large statics where the events are virtually disengaged from one another adjacent, so more than one loop apart, it helps if you use some form of forced event alignment or one of these brute force trim statics methods to align things before you actually do the smoothing. Now, this sounds like cheating a little bit, and I convinced myself earlier this year that it's not by leaving this out on some real data and was able to show that, yes, you do get to the same solution, but you may have to iterate to get there. So it's not cheating, it helps you converge. Now, other methods for creating these pilot traces are being tested. In fact, Matt Yedlin suggested to me that SVD would be a good way to do this, to take your raw gather and look at the lowest order components as maybe a good estimate of this reference wave field. So this is on the books to look at, and I haven't actually started doing it yet. Anyway, this is what pilot traces look like for this synthetic model. Look quite clean. Remember that most of what you see in here is just averaged noise. So you can now certainly see the 5 events. So when we correlate this against this, which is how we generate our surface functions, this is the kind of thing we get. These are the raw cross correlations of the synthetic traces with the pilot traces. Those don't look too promising. Can we actually generate inverse filters from these and correct the initial data? Well, the answer is yes. But we can do a better job if we refine these cross correlations by doing this whitening and conditioning that I talked about. It turns out one of the easiest ways to condition these is something suggested by Rothman when he was doing his simulated annealing statics, and that is just to raise the correlation values to a power, typically an odd power, and then I add the additional thing of simply applying a Hanning window to the correlation function so that maxima near the center of the correlations get a little more weight than those out toward the tails. When you do that, things simplify a lot, and these begin to look a lot more like simple peaks, or in fact, you could think of them as time shifts. Time shifts would work here. So this is the synthetic gather corrected using inverse filters from those raw cross correlations. Well, I think you'd have to concur that they don't do too bad a job. You can see some places where it didn't work at all, like this trace here, but in general, that worked fairly well. Now, if we use those conditioned correlations, on the other hand, this is actually the raw data, so we'll compare with the original raw data. You can see it looks pretty good. If we use the conditioned correlations, though, we can see it looks a lot better. So that's the process, the interferometry process. Now I'm going to show you a couple of quick shots here of some actual data. This is a common angle gather whose apparent velocity, the velocity parameter, is 1185 meters per second. This is what it looks like before the interferometric process, and that's what it looks like after. Well, once again, it looks less promising than you might think, but if you compare events, look particularly at this band of events up here, you can see that on this corrected gather, they're much flatter. In general, they've been better aligned. For a different common angle gather from the same data set, this is what we get. This is before, and this is after. So it looks like the interferometry is doing the right kind of thing. So let's now look at two data examples in detail. We'll look first at the Mackenzie Delta data. And as I mentioned before, this is a particular type of data that the process was designed for. There are large statics, and surface consistency is definitely violated because this is a permafrost zone, permafrost area, where the near surface velocity is typically higher than the velocity of the first consolidated layers beneath. And after many tries, it was concluded by the processors of the day that conventional statics were simply inadequate. Then I want to go to the Hussar low-frequency experiment that I mentioned that Cruise and some of its sponsors performed just over a year ago. And here, conventional statics work very well. So why would we use this complicated interferometry process? Well, I'll show you a couple of displays that I hope will show you why I'm continuing to look at it. For the Mackenzie Delta, this is the situation. There's a deep anticlinal structure that they were attempting to image, and the near surface consists of, there's an unconformity here, but furthermore there are these near surface sediments that are pretty flat lying. On the other hand, you've got the base of permafrost here that actually comes up to the surface in a place or two, and you have these channels, ice-covered river channels. They actually have liquid water in them virtually year-round. So when you shoot across them with a surface source, they generate horrendous ice flexural waves. And part of the key to processing these data is to get rid of as much of that noise as possible before doing anything with the statics. So that's the picture. This is what the brute CMP stack of those data look like. And there are the three largest river channels. There's actually one over here as well that doesn't show up as strongly. But note that this unconformity, which should be flat lying, is sagging here, and it's totally disrupted here and here. Furthermore, if you look deep in the section, you can see that, yes, these events do continue, but boy, you can't see how they connect up at all. There is coherent energy in there, but it's not lined up at all. We actually know that the statics in that zone can be as high as 200 milliseconds. So this is what a common angle gather from those data would look like. And you can see, lo and behold, the same features show up at the level of the unconformity. And you can see some hints of the steeply dipping layers beneath. Now, this is what we need to do in order to get pilot traces for our interferometry scheme. We pick a horizon here. Basically, that unconformity makes a good horizon for smoothing along. And then we pick sort of an arbitrary layer down on the anticline. And you might say that we're fudging here because you can't actually see the event, but we have good reason to believe that it does continue through, so we're going to smooth along that horizon in any case. So when we do that horizon smoothing and create pilot traces, this is what the pilot traces look like for one particular common angle gather. And remember that we'll have, for these data, I believe we have about 200 different common angle panels. So this is only one of 200. And we generate these pilot trace panels for each common angle gather. When we do that and do the interferometry, we come up with surface functions. This is a set of the surface functions that we generate for one of the common angle panels, and I want to draw your attention to this zone here. You can see the obvious functions for one river channel. This is for another, and this is for that one on the extreme right. You notice these surface functions don't look very good. For this particular common angle panel, you don't get a lot of information from these. So you're relying on information from other common angle panels to help you fill in. But the point I want to make here is we look at this little box here, and here we see now the some of the advantage of going to surface functions instead of single static shifts. We can see that we've got more than one peak for some of these surface functions. This indicates the existence of multipathing, which we know happens in the Mackenzie Delta near one of these melted zones. And a river channel is a good example of that. On the bank of the river, everything is frozen solid to the surface. As you move out into the channel, then you run into the soft melted stuff beneath the water, and you wind up with two actual transmission paths for seismic energy, the slow one through the mush and the fast one through the edge of the channel. So this indication of that, there's no way to correct that with a single shift. The only way you can correct that is get an inverse filter and deconvolve it. Okay, this is what Mackenzie Delta section looks like after applying Raypath interferometry. And I want to point out some features that you don't see on the initial root stack. You can actually see what we think is the base of permafrost right there. Notice that the flank of the anticline has been nicely connected. And furthermore, we have a lot more detail in that near surface. Now, these are things that you don't see on any of the data from this area that were corrected using conventional statics. So we consider this a vindication of using this Raypath interferometry. Now, let's look at the HASAR data. These data we'll look at first are vertical component dynamite data with 10-meter receiver spacing. We applied radial trace filtering, which I've talked about and won't go into here, but we left frequencies above 3 hertz untouched because we're looking for low frequency response from the reflections. Applied Gabor deconvolution, and we did 2 static solutions for comparison on these data that had common processing up to this point. I applied the Raypath interferometry, and Helen Isaac applied conventional move-out analysis and residual statics. So these are what the data look like before any statics correction, and I've stacked these just with a single normal move-out function, which will work for these data but is not optimum. This is the solution that Helen provided using normal move-out analysis and standard residual statics. And I'm showing a couple of zones here to keep your eye on. In particular, the detail in this particular layer here. This is what we get using Raypath interferometry. Now, I have to hasten to add that I've done a little bit of post-stack processing here, including a decon and some FX decon to remove random noise. So we're not comparing totally comparable results here. On a closer scale, this is the section conventional statics, and this is the Raypath interferometry. Now, when you go back and forth between these two, you kind of see now what I'm a little bit excited about, and that is, I think you see a little more detail in this one, particularly this zone up here, which I'm told is one of the zones of interest for the explorationists. Now, just as an aside, I'll show you that we've actually preserved a lot of frequency here. These are the amplitude spectra after that interferometry. And there's the 3 hertz cutoff, and we have frequencies, coherent frequencies, apparently down to around 3 hertz. If we look at the phase spectra, which is a better indication of that there's that same 3 hertz bar, and we see that we have coherence right down to about that level as well. Now let's look finally at the radial component of the vector size. This is inline shear. Once again, we did similar processing, only in this case, Helen did the processing herself from the ground up, and so our results are not going to be quite as comparable. This is the approximate common conversion point stack that I provided. And now I'm using a single normal move-out function and no statics. And you can see the effect of using just a single move-out function is that we show some apparent structure on this event. And we know there's none there, so this tells us right away that the normal move-out is not correct for the entire line. It works reasonably well in here, but there should be some adjustment made over here. This will get important in the next couple of slides here. Now, when Helen does the proper thing, does a correct CCP stack, does all the conventional normal move-out, and converted wave statics, we get this nice picture here. So, no structure, for sure. And I'm flagging these three events to keep your eye on as we go to the next slide, which is the results from the interferometry. Now, in spite of the fact that we only used a single NMO function, we see no structure here. So what it appears is that the interferometry also helps correct the residual move-out. And this is not unexpected because we know from our mathematical analysis of the usual statics correction process that residual move-out is not orthogonal to the surface corrections. So S and G corrections are orthogonal to each other relatively, but not to residual move-out, which is why so many statics programs do solutions for the source corrections and then the receiver corrections and then a run of residual move-out analysis because these are not totally independent. Anyway, this is the comparison. And they look fairly different this time. And I don't want to really address those differences so much as to say that this is an ongoing subject of investigation. Now back to those residual move-outs. This is a common receiver stack of the radio component. And here, once again, it's had just a single normal move-out, and so we see that, once again, this apparent structure plus these enormous statics. Furthermore, if you look here, it looks like we have as much as 300 milliseconds of static deviation, but if you look deeper, that looks more like 200. Well, another indication that the move-out has not been accounted for properly. But when we do the common receiver stack after interferometry, both effects have gone. So I've been chastised before by various individuals indicating that these aren't really non-stationary statics, even though they look like it. What it really is the interaction of residual move-out that hasn't been accounted for and an actual static. So that may well be, but my point is that the interferometry process appears to take care of that all at the same time because it's based on maximizing the stack power. So residual move-out, or NMO, is not independent of surface anomalies and may appear as non-stationary shifts. So, since the Raypath interferometry maximizes stack power, statics and residual move-out are corrected simultaneously. Now to the observations. This is what I'm finding interesting. Raypath interferometry is comparable to conventional residual statics on regular data, or possibly better. The jury is still out on that. I need to go back and enhance those conventionally processed results to see whether I can approach what I see with the interferometry. The comparison is difficult on the converted wave data because of different processing, but still, I think if you remember back to that comparison, the interferometry results did seem to have more detail, particularly in the shallow portion, than the conventionally processed data. And finally, Raypath interferometry seems to correct apparent non-stationary statics. I'm going to continue to use that word apparent. Now, data quality, in order to use this, must be good enough to see reasonably continuous event horizons so that you can actually pick a horizon to use for doing pilot traces. I dare say you could probably do this across a fault, but it would require a very careful pilot trace construction. I have not done this, so I can only conjecture that it would be possible. And where data are truly surface consistent, the technique is probably overkill. Lastly, the interferometry probably works because the traces that we generate, these common angle traces, are very similar to the so-called super traces that introduced by Ronan and Claerbout in 1985 in their notable paper describing max stack power autostatics. And to show you this, let me go back to the radial trace transform and show you why that's true. Here I'm showing you a single radial trace trajectory, and it's crossing this initial gather at some angle determined by velocity v. And actually what you're doing to put together this radial trace is, in effect, you're grabbing a segment of this trace, a segment of this trace, a segment of that trace, and so forth, and you're just appending them. Now, how you append them depends on the interpolation process. Since we're using a simple two-trace interpolation whose weighting coefficients vary from linear up to nearest neighbor over whatever parameter you select, then basically we're just constructing a supertrace. Now, the supertrace that Ronan and Claerbout talk about are trace windows selected along a common time, or at a constant time. Here, we're selecting trace segments along a common velocity. So that's how the two are similar. And it turns out that our pilot traces then are similar to the stack supertraces that Ronan and Claerbout look at as well. So when you correlate these things, as we do, then our process is very similar to the Ronan and Claerbout process. The only difference is they simply take the trace maximum and apply a shift that corresponds to that trace maximum. And that gives them this max stack power result. I, on the other hand, derive an inverse filter for that cross correlation and apply that inverse filter. And so I maintain that my results should be very much the same kind of thing, only I'm doing this in this constant Raypath angle domain. Now I need to acknowledge the sponsors of CRUISE and NSERC for our funding, Helen Isaac in particular for the data preparation and for processing our comparisons. Shell for use of that Mackenzie Delta data. Those data have been so used that they're practically worn out. And the sponsors participating in the Hussar survey for access to the data. And thank you.
Well, we've got probably about 10 minutes or so for questions, and then got some closing announcements. So before I throw it over for questions, I have a question of my own. And thanks very much for the talk, actually. I really enjoyed it. The question was regarding these pilot traces that you generate for your radial traces. And I was wondering, what kind of process do you use to ensure consistency between all the different pilot traces from one radial angle to the next?
The consistency is ensured by the fact that the angle increment is so tiny in general. Since for the Hussar data, for example, we used 1,000 radial traces, so that would give us 1,000 common angle panels. And the angle from one panel to the next does not change very much at all. So, in fact, since you're smoothing across each panel, then the pilot traces for one common angle panel will look very much like the pilot traces for another, as they should.
You don't do any additional kind of smoothing on the pilots across the different angles?
I've thought about that, and there might be some merit in that, but I've not done that. So, yeah, doing the pilot traces really is the key to this method, and you have to pick something that's as free of your prejudices as possible, I think. Hence, I backed off on that trim statics forced alignment on some data just to see whether I was in fact fooling myself and convince myself that no, that's just shortcutting the inevitable result.
Have you thought about the difficulty of doing this in 3D?
I don't even want to think about it. Obviously, if you're going to stay in this common angle domain, then you have to introduce three-dimensional surface functions, which means then you're going to be looking at azimuth as well. And at that point, I think the tedium of the method would probably outweigh any benefits. Mike?
You were saying that you could potentially interpret faults in the horizon. If it wasn't fault, would that appear in different locations on the radio trace camera?
Yes, they would. And so that yeah, if it were a normal fault, you might be able to do something. But if it's not, and most faults are not, then it would make it really difficult. Yeah.
Question about the Raypath consistent model. So when we talk surface consistent, we usually talk about source and receiver.
Yes.
When we talk Raypath consistent, obviously you have one component being the Raypath with common angle. Is the other component still the source, or is there just the Raypath component?
What I didn't mention was that when you choose which gathers to use for your first run of this, typically you'll use which gathers are best populated, and that's usually the source gathers because receivers are more closely spaced. So you do the transform from the shot domain, and that gives you then shot radial trace gathers. So what you really generate are shot common angle gathers. And so once you run through that process, if in fact you do not have surface source and surface receiver, then it's worth going to the other domain, taking the first pass of corrections, sorting to the receiver domain, and then creating source or receiver common angle panels and doing the same thing again to finish doing the corrections. So there is a difference.
Two corrections.
Yes.
But if you're doing, say, shot and common angle, would that usually suffice? Would that sort of replace what normally would be done by a receiver component?
It turns out that for surface source receiver, like the Mackenzie Delta data, in fact, one pass is often enough because for a reason I don't totally understand myself, this interferometry approach seems to provide the common static for surface locations, whether it's source or receiver. If you in fact have buried source and surface receiver, then what you'll get is the common static, but that still leaves a difference between the source and the common static that you have to get in a second pass. So the Hussar data, in fact, I needed to apply first in the source domain and then in the receiver domain to get the solution that I showed. So it's not unlike conventional statics in that regard. You often have to do first one domain and then the other. Fair enough. No, it's just trace sorting is all it is. Because the radial trace transform, the coordinate of the traces is velocity, and that is basically an identifier of the angle. So you just pick all the traces from all the gathers that have that same velocity, and that is your common angle gather. Absolutely different, yeah. I really ought to try to find some terms that don't cause confusion here. I realize this common angle gather is something that's used in migration, and it doesn't mean the same thing at all. Here, I actually, at the beginning of the talk, I talked about it's actually a parameter, so common radial parameter gather would be a more accurate way to talk about this. But I haven't done so. Maybe I should do it in the future.